In this lesson, we're going to be looking at particle motion. And we know the derivative is rate of change. So when we think about a movement or a position changing, we're looking at velocity. So the derivative of position is velocity. And since acceleration is the rate of change of velocity, then acceleration is velocity's derivative. So in calculus, f of x is increasing. Our derivative is positive, right? F prime is greater than 0. That means we're moving to the right in physics. That means velocity is greater than 0. When f prime is negative, we're decreasing. When the velocity is negative, we're actually moving to the left. Now, a relative max or a relative min. Of course, those occur when our derivative is 0, but this one occurs when we're changing from positive to negative, and this one occurs when we're going from negative back to positive, right? Positive to negative, negative to positive. This means we're changing directions when we think about an object in motion. We were moving right, and now we're moving to the left. Or we were moving left, and now we're moving to the right. Concave up. That's when our second derivative was positive. That means here our acceleration would be positive. That also means that the derivative of velocity, the change in velocity, is positive. Concave down. Second derivative is negative. Negative acceleration. You're slowing down. Your rate of change is decreasing. And a point of inflection is when the second derivative is 0. That means we're changing our acceleration. We're either speeding up or slowing down. But we're going to look at it. We'll review graphs and then apply some of these rules. So here's a velocity graph of a dot going back and forth on a computer screen. When is the dot going to the right? Now remember, this is velocity. So when is velocity positive? Well, that's from 0 to, looks like 5.5. And from about, what's that, 10.6 to 15. When is the dot going to the left? Well, when velocity is negative. When is the dot stopped? Well, when it's changing directions. So at actually, that's when it's changing directions. I wasn't reading. When is it stopped? Well, it stops at 15. That's when the velocity goes to 0 and stops. When is the dot at its highest speed? Maximum. So between 2 and 3. When is the dot moving at a constant speed? Well, constant speed would be each time it flatlines. So between 2 and 3, 4 and 5, 8 to 10, and 11 to 13. I should union those. Union, union, union. When is the dot speeding up? Okay, so remember, this is a graph of velocity. So when is velocity accelerating? Well, that's when we're speeding up. We're going from 0 velocity to 4 velocity. And then again, from 10 to 11. When is the dot slowing down? So our velocity is decreasing. That would be from 3 to 4, from 5 to 6. Oh, continuing from 6 to 8, and then again from 13 to 15. When is the dot's velocity positive? Well, we already had those down. That's when the dot is going to the right, from 0 to 5.5, and then again from 10.6 to 15. When is the velocity negative? When is the dot's acceleration positive? We already marked those. That's when it was speeding up. When is the dot whoops, I drew my line too far. When is the dot's acceleration negative? Well, we wrote those down too. Those were here. When is the dot accelerating the most? Ooh, that'd be the steepest, right? The biggest slope. So let's look. Here it's going up 4 over 2. 1, 2, 3, 4, 5 over 1. It's between 10 and 11. And what is the acceleration at that time? Acceleration is that rate of change. What do we say? 1, 2, 3, 4, up 5 over 1. So is 5. The following function is the velocity of a dot going back and forth on a computer screen. So we have the same thing. We have the function for velocity. So we need to know some critical values. When is that velocity 0? And that type of thing. So to get some critical values, might be helpful to factor. See, we have a t in common. Two things that multiply to be 40, 8 and 5. So our critical values for velocity are 0, 5, and 8. We also need to think about the critical values of acceleration, which would be the second derivative. The derivative of velocity. So let me come up to the side. Acceleration would be the derivative of velocity. That'd be 3t squared minus 26t plus 40. Okay, so remember, I'm wanting to make sure I find my critical values for acceleration as well, which means I need to factor this. I tend to use the factor box if you have not seen it. It's really factoring by grouping. The middle terms from FOIL, from outer and inner, are going to add to be negative 26 and multiply to be 120. Well, that's 20 and 6. So I've got negative 20t and negative 6t. 3t has to go here. That's going to be a negative 20 and a positive 2. So this factors into 3t minus 20 and t plus 2, which means I have a critical value at, whoops, I messed up somewhere. That should have been minus. At 20/3 and at 2. So 20/3 is about 6 and something. So let's go ahead and 1, 2, 3, 4, 5, 6, 7, 8. Excuse me. 7, 6, 5. So here's where velocity is 0. Oops, I should have gone all the way to 10, huh? 10. So we're looking at it all the way from 0 to 10. And my critical values for acceleration are at 2 and at 6.67 or 20/3. So what this tells me, since I have these 3 critical values or zeros of velocity, if I was going to sketch a velocity graph, I know it would go up. Well, it's going to hit a maximum there, and it's going to go here. It's going to hit a minimum there, and it's going to hit there, and it's going to go off. So when is the dot going to the right? Well, between 0 and 5 and 8 to 10. Remember, that's our boundary is 10. When is it going left? Between 5 and 8. You know what? The dot does stop when it changes directions. So I'm kind of messed up on that other one, huh? And at t equals 8. Those are also when it changes directions. Is there ever a time when you would have the velocity at 0 and it doesn't actually change directions? Yeah, if it bounced. When is the dot at its highest speed? Well, the highest speed would be at a maximum, and the maximum would be here when the acceleration is 0. When is the dot speeding up? That's when the acceleration, so when our velocity is increasing, so there, from 0 to 2. And then again, going up that way. So from 20/3 to 10. When is the dot slowing down? That's when velocity is decreasing. So that's from 2 to 20/3. When is the dot's velocity positive? Well, we already covered that. That was from 0 to 5 and from 8 to 10. When was the velocity negative? That's when it's below the x-axis from 5 to 8. When is the dot's acceleration positive? Well, that was from 0 to 2, and then from 20/3 to 10. Whoops. Yep. And then when is acceleration negative? It's between 2 and 20/3. When are we accelerating the most? So which interval gives me the biggest acceleration? So when is the dot accelerating the most? Well, that would be at our highest point of acceleration. So we know our acceleration is 0 at 2 and 20/3. But when is acceleration going to be at its highest? Well, that would be when the derivative of acceleration equals 0, and then we can check to see if that's actually a high point. So let's write down acceleration over here. It was 3t squared minus 26t plus 40. So the derivative is 6t minus 26. That is 0 when t equals 26/6, which would be 13/3. Well, let's see if that is indeed the dot's acceleration is maximum. 3 times, I'll leave it as 26/6 squared minus 26 times 26/6 plus 40. That actually gave me a negative acceleration. We're going to come back to this one.